3.5 Forces acting between molecules. Atoms in molecules and in giant structures are held together by strong covalent, ionic, or metallic bonds. Molecules and separate atoms are attracted to one another by other, weaker forces called intermolecular. Inter means between. If the intermolecular forces are strong enough, then molecules are held closely enough together to be liquids or even solids. There are three types of intermolecular forces, and I'll now name them from the weakest to the strongest. We start with van der Waals forces. Those act between all molecules and all atoms. Then we have dipole-dipole forces. These act only between certain types of molecules. And finally, hydrogen bonding, which, just like dipole-dipole forces, acts only between certain types of molecules. Now, to the dipole-dipole forces. Polarity is the property of a particular bond. See topic 3.4. But molecules with polar bonds may have a dipole moment. This sums up the effect of the polarity of all the bonds in the molecule. In molecules with more than one polar bond, the effect of each bond may cancel, leaving a molecule with no dipole moment. The effect may also add up and so reinforce each other. It depends on the shape of the molecule. For example, carbon dioxide is a linear molecule and the dipoles cancel. Tetrachloromethane is a tetrahedral, and here too the dipoles cancel. But in dichloromethane, the dipoles do not cancel because of the shape of the molecule. Dipole-dipole forces act between molecules that have a permanent dipole. For example, in the hydrogen chloride molecule, chlorine is more electronegative than hydrogen. So the electrons are pulled towards the chlorine atom rather than the hydrogen one. The molecule therefore has a dipole and is written as H, small delta, plus, Cl, small delta, minus. Two molecules which have both dipoles will attract one another. Whatever their starting position, the molecules with dipoles will flip to give an arrangement where the two molecules attract. Van der Waals forces. All atoms and molecules are made up of positive and negative charges, even though they're neutral overall. These charges produce very weak electrostatic attractions between all atoms and molecules. These are called van der Waals. So, imagine a helium atom. It has two positive charges on its nucleus and two negatively charged electrons. The atoms as a whole is neutral, but at any moment in time, the electrons could be anywhere. This means that the distribution of charge is changing at every single instant. Any of the arrangement in figure 2 mean the atom has a dipole at that moment. An instant later, the dipole may be in a different location, but almost certainly the atom will have a dipole at any point in time, even though any particular dipole would be just for an instant, a temporary dipole. This dipole then affects the electron distribution in nearby atoms, so that they are attracted to the original helium atom for that instant. As the electron distribution of the original atom changes, it will induce new dipoles in the atoms around it, which will be attracted to the original one. These forces are sometimes called instantaneous dipole-induced dipole forces, but this is rather mouthful. The more usual name is van der Waals forces, after the Dutch scientist Johannes van der Waals. Now, van der Waals forces act between all molecules or atoms at all times. They are in addition to any other intermolecular force. The dipole is caused by the changing position of the electron cloud, so the more electrons there are, the larger the instantaneous dipole will be. Therefore, the size of the van der Waals forces increases with the number of electrons present. This means that atoms or molecules with large atomic or molecular masses produce stronger van der Waals forces than atoms or molecules with small atomic or molecular masses. This explains why the boiling point of the noble gases increase as the atomic numbers of the noble gases increase. The boiling point of the hydrocarbons increase with increased chain length. And the last of the main intermolecular forces, hydrogen bonding. Hydrogen bonding is a special type of intermolecular force with some characteristics of dipole-dipole attraction and some of covalent bond. It consists of a hydrogen atom sandwiched between two very electronegative atoms. There are conditions that have to be present for hydrogen bonding to occur. You need a very electronegative atom with a lone pair of electrons covalently bonded to a hydrogen atom. Water molecules fulfill these conditions. Oxygen is much more electronegative than hydrogen, so water is polar. You would expect to find weak dipole-dipole attractions, but in this case the intermolecular bonding is much stronger for two reasons. One, the oxygen atom in water has lone pairs of electrons. Second, in water, the hydrogen atoms are highly electron deficient. This is because the oxygen is very electronegative and attracts the shared electrons in the bond towards it. The hydrogen atoms in water are positively charged and very small. These exposed protons have a very strong electric field because of their small size. The lone pair of electrons on the oxygen atom of another water molecule is strongly attracted to the electron-deficient hydrogen atom. This strong intermolecular force is called a hydrogen bond. Hydrogen bonds are considerably stronger than any dipole-dipole attraction, though much weaker than a covalent bond. They are usually represented by dashes. Now, water is not the only example of hydrogen bonding. In order to form a hydrogen bond, there must be the following. A hydrogen atom that is bonded to a very electronegative atom. This will produce a stronger partial positive charge on the hydrogen atom. And a very electronegative atom with a lone pair of electrons. These will be attracted to the partially charged hydrogen atom in another molecule and form the bond. The only atoms that are electronegative enough to form hydrogen bonds are oxygen, O, nitrogen, N, and fluorine, F. For example, ammonia molecules, NH3, form hydrogen bonds with water molecules. The nitrogen-hydrogen-oxygen system is linear. This is because the pair of electrons in the NH covalent bond repel those in the hydrogen bond between nitrogen and hydrogen. This linearity is always the case with hydrogen bonds. The effect of hydrogen bonding between molecules can be seen if you look at the boiling points of hydrides of elements of group 4, 5, 6 and 7 plotted against the period number. The noble gases show a gradual increase in boiling points because the only forces acting between the atoms are van der Waals forces, and these increase with the number of electrons present. The boiling points of water, H2O, hydrogen fluoride, HF, and ammonia, NH3, are all higher than those of the hydrides of the other elements in their group, whereas you would expect them to be lower if only van der Waals forces were operating. This is because the hydrogen bonding is present between the molecules in each of these compounds, and these stronger intermolecular forces of attraction make the molecules more difficult to separate. Oxygen, nitrogen, and fluorine are the three elements that are electronegative enough to make hydrogen bonding possible. Although hydrogen bonds are only about 10% of the strength of covalent bonds, their effect can be significant, especially when there are a lot of them. The very fact that they are weaker than covalent bonds and can break or make under conditions where covalent bonds are unaffected is actually rather significant. In water in its liquid state, the hydrogen bonds break and reform easily as the molecules are moving about. When water freezes, the water molecules are no longer free to move about, and the hydrogen bonds hold the molecules in fixed positions. The resulting three-dimensional structure resembles the structure of diamond. See topic 3.7. In order to fit into this structure, the molecules are slightly less closely packed than liquid water. This means that the ice is less dense than water and forms on top of ponds rather than at the bottom. This insulates the pond and enables fish to survive throughout the winter. This must have helped life to continue in the relative warmth of the water under ice during the ice ages.